that's the last you'll hear from me. Thank you.
Oh, all right. Thanks, Andy. Yeah, so I guess fill out that form or something. Yeah, that'll be great. All right, guys. So, my internet is like not great today. So if I'm ever like cutting out or you can't hear me clearly or you need something to be repeated, just let me know because yeah. All right, so let's start with a whiteboard. And today I think we're going to go over something fun, I guess, which is bases or base conversion. Oh, it's okay. So anytime like I cut out or you can't hear me or something, just let me know and I'll repeat it for you. All right. So base conversion. We can start by looking at the numbers that you know, right? You can just list them out. List out some numbers that you know, or in order preferably, starting from maybe 1, right? There's 0 and then there's 1 and then there's a couple more numbers and stuff. Like, so what are the numbers that you know? Feel free to put in chat just like some numbers from 1. Like, I'll give you a hint. The next one is 2. Three, yeah, that's a number. Or a positive integer, yeah. Okay, and then the next is 4, 5, 6, 7, 8, 9, 10. And then when we get to 10, it gets interesting, right? Because for 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, there's a symbol for each of them. But when we get to 2, or when we get to 10, it's just 2 symbols put together. There's a 1 symbol and a 10 symbol, or and a 0 symbol. So what does this mean? Right? Why do we just put them together? How do we know, like, if we just choose some random numbers, how do we know what this is? What does this mean? Does this mean, right, 1, 10, and 0 ones. So basically we can write this as 1 times 10 plus 0 times 1, I guess. Or if we want to be fancy about it, we can put 1 times 10 to the 1 plus 0 times 10 to the 0, right? And looking at this group of numbers, this is actually 5 times 10 to the 2 plus 4 times 10 to the 1 plus 3. Does that make sense, guys? Like, these are just what the numbers mean, or this is what it means when we put these number symbols together, right? So everything that we're doing right now is in base 10. I think some people call this the decimal base or something. Anyways.
Hey, Ethan is 3 to 2. Yeah. It's 3 to 2.
All right. Sorry about that if you heard that. Right. Right, sorry about that. Okay, so now we can go and see base 2, right? How do I add another page? Here. Actually, give me a moment. Let me.
This meeting is being recorded.
Wait, do you think my audio is better from here? All right, okay. Okay, so now let's consider some more numbers, right? Oh, you can't see my camera? I'm just leaving it off for now because it's easier with the I'm writing it on an iPad, so it's just easier like that. Right? All right. Okay, so where were we? Oh yeah. So we finished this is base 10, right? And then if we move on, we can see that some of these numbers are can be in different bases. You guys just had Andy talk to you guys, right, about computer coding. And in computer coding, they use a bunch of ones and zeros, right? So if in some world, the only numbers that we have are 0 and 1, that's and we want to be able to count with these numbers, right? We go 0, 1, and then what? There's no 2, right? 10, right? Yeah, that's right. And then 11, and then 100. But we don't call these 10, 11, 100. It's just 0, 1, 1, 0, 1, 1, 1, 0, 0. And if we use our normal numbers, we have 1, 2, 3, and 4. But since these numbers 2, 3, 4 don't exist in what we would call base 2 or binary, they don't exist. So we have to use our old numbers 0 and 1 instead, right? So when we look at this, what does it mean? What does it mean when we put 1 and 0 together? We remember that in base 10, this meant 1 times 10 to the 1 plus 0 times 10 to the 0. But what does it mean in base 2 or binary? Right, okay, that makes sense. So here in binary, 10 base 2, it's equal to 1 times 2 to the 1 plus 0 times 10 to the 0. Or, whoops, sorry, 2 to the 0. Right? So if we make some big number like 10110, well, it's not really big, but what would this be equal to in our binary system? 22? Oh, 10 base 6 equals 6. Oh, yeah, 10 base 6 equals 6. Yeah, basically. 22, let's see. You know it's 0 times 2 to the 0 plus 1 times 2 to the 1 plus 1 times 2 squared plus 0 times 2 cubed plus 1 times 2 to the 4, right? So that's 16 plus 4 plus 2 equals 22. Yeah, so it's 22 in base 10, right? But it's 10,110 in base 2. So that's kind of how bases work, right? If you have a number, let's say A with some spaces, let's say 3, and then you have it in base x, this is basically meant to be A times, or let me use the dot, A times x to the what power? 3, right? This is A times x to the 3. And if we have A, B, C, D, it's A times x to the 3 plus B times x squared plus C times c times x plus d, right? Well, times x to 0. All right, so if we have this, we can express different numbers in different bases, right? If we want to have everything in base 6, we'll know how to convert it because it's just expressed in this form. Now, what if we have a number, let's say, in base like 12 or something? We know the symbols for 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. But this is in base 10, right? So there's 10 numbers. But if it's in 12, there should be 12 numbers, right? So what do we do? Or does anybody know what we do? A and B. Yeah, that's right. So we'll start adding letters instead. Right? So this is essentially 10, but not 10. It's like the value 10, but not in base 10. I don't know if that makes sense. We might use it in some later problems, but for right now, you probably don't need it. All right, so if we make another page, we want to be able to express, let's do some practice problems, right? Let's say I have 213 in base 10, and I want to convert that to base 5. What would this be equal to? Just to make sure everybody knows how to do this. Oh, actually, I think this is harder. Let's start with 213 base 5 to base 10. Right? All right, so somebody asked, what if we have base 38 or something that needs more numbers than all the letters and numbers we have now? I probably can't give you an answer to that right now, but most of the time we work with numbers, and the highest that we work with normally goes up to base 16. I don't think that you'll find many math problems that go and use bases higher than that. But yeah, I don't actually know. I've never worked with anything like that before. I guess you could Google it. But yeah, I don't really know. Sorry. All right, let's look at this. 2, okay. So we know this is 2 times 5 squared plus 1 times 5 to the 1 plus 3 times 5 to the 0, right? Because in the rules of base, or in the rule of bases, we know that since this is in the third place, right? This is in the first, second, third. It's 5 squared, right? So instead of naming it 1, 2, and 3, we can name it 0, 1, and 2, right? And when we have numbers, it's 0, 1, 2, 3, 4. And this is the base that you multiply in. So you start from 0. No, 58. Yeah, this is equal to 58 in base 10. I'm saying that this is like this is the power that you multiply, right? So this is multiplied by something to the 0th. This is multiplied by x to the 1. This place is multiplied by x squared. Does that make sense? Like, it's the digit in this position. And we also know that in bases, it goes up from 0, 1, 2, all the way to x minus 1 if it's in base x, right? Right, in base 2, we only had 2 numbers, 0 and 1, so it only goes up to 1. And if it's base 3, it's 0, 1, and 2. So it never goes up to the number that it's in, right? The base number that it's in. So those are just some ground rules for this. Yeah. Let's look at 679 base 10, and we want to convert this to base 6. It'll be a little harder since you start with this and you don't just want to guess numbers. Well, you could, but it'll take a long time. Instead, what you should do is division, right? So 679 is equal to A times 6 cubed plus B times 6 squared plus C times 6 plus D, right? You don't actually know if it goes up to 6 cubed. It might even go up to 6 to the 4th or something, but we don't know. Instead, we see that this part is all divisible by 6, and this is the only part that's not, right? D. So D would be the remainder of D would be the remainder of 679 divided by 6. Does that make sense? Oops. So 679 divided by 6 equals to 7, I think. So we know that the last digit is 7. Oops. Or it's 1. Yeah, sorry. I don't know why I thought it would be 7. It's 1. So 679 divided by 6 is something, and then but the remainder is 1. Right? So when we do this kind of division, it's easier to make it look like this. 679 divided by 6. Instead of looking at the usual fraction way, we can use this dividing symbol to get 1, 1, 3, I think. And then we can just do another division table on top of that, right? And then it's, I think, is that right? Yeah. Right? So if we look at this, it might not look like it might not make any sense at first, but you can see that it's 679, and then you divide it by 6 and you get 113 remainder 1, and then you divide that by 6 again, right? Because this part is divisible by 36 and this part is not. So you just keep dividing until finally you get 0, and then you take this number, and this is the number that it's in base 6. So it's 3051 base 6. Does that make sense? Like, this is a cool trick using we can use to convert base 10 numbers to other bases. It's a cool trick. It's pretty fast. Of course, there are probably faster ways, but does everyone understand how we convert numbers? Oh, you don't understand? That's okay. Let's make a new page, right? Let's just consider this example. What was the number that we had? 679. Right? And we know that this is from A times 6 to the 0 plus B times 6 to the 1 plus C times 6 squared plus D times 6 cubed plus E times 6 to the 4th, and so on, right? Does that make sense? This part makes sense? Yeah? All right. So when we look at this, we know that this part is all divisible by 6. So this is the remainder, right? So when we divide it, so the remainder is 1, right? So it's 1 times 6 to the 0, because 6 to the 0 is 1. Anything raised to the power of 0 is 1. All right. So if we have that this is 1, we have this entire part, right? But we know that this part is all divisible by 36. because 36 is divisible by 36, 216 is divisible by 36, and so on. So we know that this is the part that's not divisible by 36, but we already know what this part is, right? It's 1. So we want to find this part. We know that this sequence, when we divide it by 6, so it's b times 6 to the 0 plus c times 6 to the 1 plus d times 6 squared, and so on, right? This part is equal to 113. And again, we see that this part is divisible by 6. So this part is the remainder. And if we divide this part by 6, we get 18, I think, and the remainder is 5. So we know that b equals to 5. And again, if we, right, it makes sense now? All right. Does anybody else have any questions? All right, this seems like no questions. All right, so we took quite a bit of time doing this. We might not be able to get to all of the problems that I have. So we might skip a couple of the first few problems. Let me see though. Let's look at this first problem, and then I'll see how much time we have from there. Again, we just did some exercises converting to and from base 10. If you know how to do that, I think this will be okay for you, but it'll get harder as we go on. Okay. We're getting some answers in chat right now, so I think we can go over this problem. Right. So some of you guys are getting this right. It's base 6 That's correct. But let's look at this, right? For what base is the representation of 285 a 4-digit number? So let's say that it's A, B, C, D, and base X, right? And this is equal to 285 base 10. So A times X cubed plus B times X squared plus C times X plus D equals 285. So we know that 285, let's look at some. So we know that 4 to the power of 4 is 216, or sorry, 256, and then 5 to the power of 4 is 625, and 3 to the power of 4 is 81, right? So we know that this number is less than x to the power of 4, since if it was to the power of 4, then there would be another digit in front, but there isn't. So it must be less than that. Now that means that oh yeah, between 4 and 7. Right. So if we consider the cubes, we have 5. Oops. 5. 5 cubed is 125. 6 cubed is 216. 7 cubed is, I think, 343, I think. Yeah, that makes sense. So we know that this is between x cubed and x to the 4th. So it has to be greater than 256, and it's less than 343, right? So it's either 5 or 6 for a 4-digit number. And then when we look at this, we know that D is not divisible by X, right? So 285 divided by 5, the remainder is 0, and 285 divided by 6, the remainder is 3, I think. So the final digit has to be odd. If it was in base 5, the final digit would be even, but if it's in base 6, the final digit would be odd. So it has to be in base 6. Does that make sense, everyone? Right. Yeah, that's true. If X is even, then D is odd. Since if X is even, this entire part is even, and D is odd, then 285 is odd, because an even plus an odd is an odd. If this entire thing was, yeah, this is odd, and this is odd, and then this is even. Oops. Right, so does that make sense, guys? How we got base 6? If we convert it, we don't have to convert it. You guys can do that as an exercise or something, I guess. It's not necessary to this problem. Yeah, so everything gets this question. That's good. We have half an hour left. Let me think. Right, I guess we'll skip these 2 problems and we'll go immediately to this problem. This is a nice problem. Right. Okay, Kevin. That's something that's really important to note. N squared plus 2n plus 1 is equal to n plus 1 squared. So keep that in mind as you think about this problem. This problem is kind of a trick question, which I guess is a hint or something. But yeah, this is like a trick question. You know what? I think we'll just start solving it right now. Right. Do you guys want more time to think about it, or do you want me to just explain it right now? More time? All right, I'll give you guys another minute. All right, this looks like a good time to start. How many integers n? So remember what Kevin said, and we have that n plus 1 squared equals n squared plus 2n plus 1, right? We'll just keep that in mind. Let's look at 121. 121n if we write this in base 10, we have 1 times n squared plus 2 times n plus 1 times n to the 0. And we can see that this is equal to n squared plus 2n plus 1. And if we think back, these two look equal, right? So 121 n equals to n plus 1 squared. And we want to know how many integers n between 3 to 10. So if we have 3, 4, 5, 6, all the way to 10, we want to know how many numbers are here. And if we just subtract 2, it goes from 1 all the way to 8, which is 8 numbers. So it's 8 numbers, right? Does that make sense, everybody? The hint was that this is true. N squared plus 2n plus 1 is n plus 1 squared. So they're all a perfect square. All of them, from 3 to 10. This was like a nice, simple problem to start you guys off. Are there any questions? All right, so this looks good, and we can move on to the next problem. I'll give you guys a couple minutes to think about this one, and we'll go over it. It's really similar to the previous problem, so maybe we can move a little bit faster. All right, guys, does everyone think that they're good to finish the problem? Or I mean, I can finish the problem. And yeah, Kevin, that's right. Good job. All right, so I think everyone is okay with me explaining now, right? All right, yeah, so it looks like more answers are coming in. 17, that's right. Right, so b squared equals 121 base c, right? And using what we know from the previous problem, this is c plus 1 squared. And since b squared equals c plus 1 squared, and we know that b and c are both positive, b equals c plus 1. That's good enough for now. If we have c squared equals 71 b, or in base b, we have that c squared equals 7b plus 1. And we know that c squared, b minus 1 equals c from here. If we plug this in, we get b squared minus 2b plus 1 equals 7b plus 1. And if we combine like terms, we get b squared equals 9b, so b equals 9. Easy enough, right? And then we have c equals b plus 1, or b equals c plus 1, so c equals 8, and b equals 9, so if we add them up, we get 17. So this was easy enough, right? Does anybody have any questions, or was everyone good with this? Yeah, we're good? All right. Maybe we can do this problem, or maybe we'll start with this problem. No, I think this problem's easier first. Also, I think everyone should give a feedback. This last day is supposed to be like a fun day with base conversions. If you have any questions about anything, please let me know. And if you think I'm going too fast or too slow, you can let me know. Since it's the last day of the 4-week camp or something, I'd like feedback or whatever. Am I going too fast, too slow? Are the problems too hard, too easy? And I think you guys can give that in the survey. In one of the surveys. In the survey, yeah. Andy put it in the chat earlier, but if you guys still need it, let me know and I'll copy and paste one. But please fill out the survey if you have time. It helps us get feedback. And yeah. Right. So I always explain them if they're too hard. Yeah. So the point of this is so that you can learn more concepts and be more comfortable with harder problems. If they seem too hard for you before or you get them wrong or something, I'm here to like help you understand how to go about solving the problem and how to get to the right answer. And you can apply like those kinds of techniques in future problems that you'll see, because a lot of the problems in AMC10 are pretty similar. All right. But everybody go fill out the survey, but probably after class though. Yeah. I'll give you like a minute more to like look at this problem and then we'll go over it. All right, so we're going to be going over the problems now. Yeah, so 6 is correct. It's a variant of base 5. Yeah, that's correct. So let's think about the problem, right? If we have boxes. We start with how many balls? I think we start with 1, right? We put 1 in the first box. And then we have 2, and this is 3, and this is 4. Now on the 5th turn, we see that we have to erase all of these and put 1 in the first box that still has room. Here. So instead of thinking that we're taking them away and putting it in the first box that has room, instead we can think that the balls in this box groups together to form a bigger ball, and we put it in this box, and then these balls all form together and put them here, right? And we see that this is true because if this box is filled, the next step, you put 1 in the first box that has room and you empty this one. So basically, it's filling this up until it's full and then transferring them as 1 into the next box. And we can kind of see that this is base numbers, right? Because this is 1, this is 2, this is 3, this is 4, and then we get 1, 0, right? Because there's no more here. So we know that 1, 0 has to be equal to 5. So that means that 10 in base 5 is equal to 5. So we know that this problem is in base 5, right? Since it goes up to 4. Now we have 210 steps, and we want this in base 5. So if we do the division tree or something, I don't know, we can call it a tower, I guess, like the division tower. If we divide it by 5, we get 402 remainder 0. And then if we divide by again, we get 80 remainder 2. And if we divide again, it's 16 remainder 0. This is 3 remainder 1. 0 remainder 3. So this is our number, right? 31020 base 5. And we want to know how many balls in total in the boxes. So 3 plus 1 plus 2 equals 6. Does that make sense? Yeah? That's good with everyone? All right. So this was a fun problem. I think you'll see a lot of problems that are boxes and balls that are essentially base problems. Essentially, they are something in a different base that you guys can express in, I don't know, base 5 or base 6 or something, and it's disguised as a counting number, like having balls and boxes. Sometimes it's not in bases, but in those scenarios, you'll basically use the concept of bases to help solve the problem. Right. Oops. We have 10 minutes left. I don't You guys can do this problem as homework or whatever, but let's look at this problem. This is a fun problem. I'll let you read it like that, and then we'll look at it later. Okay, so this looks like a long time, and you guys have been able to think about it for a little bit, but I don't think anybody solved it yet, so let's solve it together. So we have C, add, and C. If we add them together, we get base. Right? And this is in a different base. So let's say it's on base B. So S plus A plus B is S, which doesn't make a lot of sense, right? But it's in base B, so if it was S plus B, then it would carry over to the next one. Like how if it adds up to 10, then it carries over. And this makes sense. So A plus B equals B for the carryover. Now, if we look at this one, the next one, we can add a 1 here for the carryover. We have 1 plus A plus B plus E equals S plus B, right, for the carryover. So we have 1 plus E equals S, and then 1 will carry over. Whoops, I think I made this too small. Or I made this too big. Whatever. I guess I'll just 1 plus. All right. So 1 plus E equals S from the carryover. Now, if we put a carryover here as well, we have 1 plus E. Why can't it be more than 1 carryover? Right, we can think about it. If this S plus B plus A is equal to S plus 2B, then B and A both have to be B, but that's impossible, right? Because it only goes up to B minus 1. So A plus B only is 2B. And if we look at this one, if we already know that this is equal to B, maybe 1 plus E equals S, right? And S is 0. And E is B minus 1. That could work, right? Except S is the leftmost number, so it can't be 0. Like, you can't start a number with 0. Does that make sense? I'll just assume that made sense, but if you need me to clarify, it's okay. So let's clear this for a minute, and let me write it smaller. Right, so there were right, so it was 1 carry over here and 1 carry over here. Now we have E plus S plus 1 equals A. We already know that this is E plus 1 equals S. Yeah, I already had it written down. Is that not correct? It's here. 1 plus E equals S. Right, and we know that 1 plus E equals S, so E plus 2S equals A. And we know that this is probably bigger than A, right? Since, but well, actually, we don't know that. So if we assume that E plus 2S equals A, we also know that from here, oh yeah, sorry. Yeah, thanks, Thomas. I don't know why I just forgot that. I guess I had like a brain freeze moment. But E plus 2S equals A. But if there's no carryover, then S will have to be equal to S, which in this case, S is equal to B. So S plus 1 equals B. So there must be a carryover. Or it doesn't have to be 1. It could be 2 too. So we don't actually know what number it is. But anyways, so this has to be equal to B or plus 2B, right? Since the greatest value E can have is D minus 1, D minus 1, D minus 1, which, or B, sorry. So this is 3B minus 3 plus 1, 3B minus 2. So this can't be 3B because the greatest value this is 3B minus 2, right? So it's either B or 2B. If we assume that it's B, right? E plus 2S equals A plus B. We'll have A plus B equals B, E plus 1 equals S, S plus 1 equals B, and 2E plus, or E plus 2S plus A equals B. Or sorry, this should be minus A. Right? Does everybody see where these equations come from? Yeah? All right. So we can substitute this and we see that E plus 1 is S and S plus 1 is 2 is 1. S plus 1 equals B. So E plus 2 equals B, right? Yeah. If we substitute B as A plus B, we have E plus 2S equals 2A plus B. And we know that E plus 2 equals B, so 2S equals 2A plus 2, right? Since we substituted this for E plus 2. And here we have S equals A plus 1. However, we know that S equals E plus 1, and we know that each letter describes a distinct digit. So this doesn't work because this would imply that A equals E. Does that make sense, everybody? Yeah? So this can't be true. So thus, 2S plus E must equal to A plus 2B. And let's clear this. So we have A plus B equals B. E plus 1 equals S. S plus 2 equals B. And 2S plus E equals A plus 2D. Oh, sorry. Yeah, I mean B. And if we substitute some things, we get 2S plus E equals A plus 2A plus 2B. Right? 2S plus E equals 3A plus 2S plus 4. Or 2S, well, there's not 2S anymore. E equals 3A plus 4. So does anybody want to give me the next equation that we need to find in order to figure out the solution? It's okay. Let's look at this on a timeline then. So we have A is lowest, E is 3A plus 4, S is E plus 1, so it's 3A plus 5, and B is S plus 2, so 3A plus 7. (3A plus 7). Right, so we want to find the solution. If A equals 0, then B has to equal B, right? But obviously the numbers only go up to B minus 1, so A has to be at least 1. If A equals 1, then E equals 7, S equals 8, and B equals 10, I think. So this means that it's in base B with A plus B equals B, so the base is actually sorry, I don't know why my pen keeps breaking, but the base is 11, right? So we want to find the combination lock of C, which is in base 11. Oh yeah, that's a good point. If A equals 2, then S is not a decimal digit. Yeah, so that's why A equals 1. If A was equal to 2, then S would be 11, which is not a decimal digit. And S, E, and A are all decimal digits. But I'm trying to get my pen to work so I can convert, or it's not converting, but so I can write out SEAC is 871, which is the final answer. I think my pen ran out of battery or something. Whatever. So we all know that we figured out the digits that it represents, and C is equal to SEA 871. So the lot combination is 871. Does that make sense, everyone? This was a little bit of a harder problem. Sorry, guys. And it was harder than I expected. So sorry about that. But yeah, this is kind of a complicated problem, but using bases, it's not that difficult. It's just you need to simplify and rearrange the equations a little bit. All right, so it seems that Kevin and maybe Thomas were following this solution. Does everybody else think it's okay? Yeah, it makes sense. All right. Oh, there it goes. So 871 is our final answer, and it's in base 11. Or not base 11, but the problem was in base 11. Our final answer is 8 decimal digits. So I think I'm gonna let you guys go right for now. Maybe I'll see you guys next year if Kid Teach Kid decides to have a summer program again next year. But I hope you guys had fun learning about bases and about AMC10, and I hope you guys do very well the upcoming AMC10. Good luck and have a good summer. Yeah. All right. Yeah, thanks, Tanya, Thomas, Alexandra. Have a great summer. Goodbye.